Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be looking at the strong nuclear force, fusion, and fission. But specifically, the question is, what keeps the nucleus of an atom together? So, something that you should remember just from basic physics or anything in chemistry that we've talked about already is that like charges repel, right? So, if I put two protons next to each other, they should repel and push each other apart because protons are positively charged. If they get too close to each other, they'll repel. Same thing if I put two electrons near each other. And we already kind of talked about that when we were looking at electron configurations and we were looking at electron orbitals. So we've kind of already talked about this part, but we haven't talked about how a nucleus can even exist, right? So if you have two positively charged particles near each other, they should theoretically push each other apart. So what's keeping them together? And then this last case is what keeps electrons and protons together, right? So a proton is going to be attracted to an electron because they're opposite charged. So what keeps them together? Now, there's a force. It's called the strong nuclear force, and it was discovered, well, now it's a long time ago, but in the terms for like all of atomic discoveries, it was discovered very recently. And so that is what is actually holding together protons to each other in the nucleus of all of the atoms of anything in the universe. And so theoretically, like it says here, electron repulsion should strain the nucleus, breaking it into pieces, but there is a strong nuclear force that is literally gluing and keeping them together. So this force is about 100 times stronger than electrical forces and magnetic forces. So it is extremely powerful. However, it only works at the atomic level. So if we get bigger than an atom, this force no longer really functions. It only works when we're looking at tiny, tiny subatomic particles. So Albert Einstein's most famous equation, right? Everybody knows it. E equals mc squared. So E equals mc squared was a discovery that kind of applies to the strong nuclear force. So what was Einstein's discovery? Einstein's discovery was as follows. So we've talked about alpha particles already, right? An alpha particle or an alpha decay particle or whatever you want to call it is a helium nucleus, right? So it contains two protons and it contains two neutrons. We can weigh an alpha particle. So pretend that we had a really, really accurate scale and we put an alpha particle on it. If we were to weigh a single alpha particle, it would weigh 4.00153 atomic mass units. But if I take those same particles that make it up, two protons and two neutrons, and I were to weigh them individually instead, the mass of each individual portion when I added them together would be 4.03188 atomic mass units. So what you should notice here is that there is a loss of mass. So simply by holding together these particles in the nucleus, we have lost mass in some way. And so that seems like it violates the law of conservation of matter, right? The law of conservation of matter says that, matter doesn't just disappear, mass doesn't just disappear. But here it seems like that does occur. So Einstein found that when you lose some of that mass, there is an equal amount of energy that is being made, if that makes any sense. So what he called the loss of mass was a mass defect. And so in E equals mc squared, the m stands for mass defect. And so that missing mass had to go somewhere though, right? So instead, that mass was converted directly into energy. And so E equals mc squared is kind of showing us that mass or matter and energy are directly related to each other, and that matter can be transformed into energy, and that energy can be transformed into matter. It's just those things need to be conserved. So yes, energy has to be conserved. Yes, matter has to be conserved because they are two parts of the same thing. So Einstein called this nuclear binding energy. In fact, he didn't call it nuclear binding energy, but that's what we call it. We call it nuclear binding energy. And so now what we term the strong nuclear force is basically what binds together the nucleus. And so mass and energy are equivalent and can be converted into one another back and forth indefinitely. And that is, again, kind of just a little backstory to the strong nuclear force. or the nuclear binding energy. So E equals mc squared. E stands for the nuclear binding energy. M, mass defect. C, the speed of light. And so in case you forgot, the speed of light, right, is 2.99 times 10 to the 8th meters per second. So if we're squaring that, we're going to get a ridiculous amount of energy, right? So think about this. Energy equals mass defect. So even if we're looking at a tiny, tiny little atom, and then we're multiplying that mass by the speed of light squared, we're going to get a ridiculous amount of energy that is being made or conserved. Now, let's talk about nuclear fission versus nuclear fusion. So nuclear fission was discovered in 1938 by Lise Meitner. There is an element on the periodic table named after her. And again, nuclear fission is just one of those things that kind of led to the atomic bomb. So what is nuclear fission? Nuclear fission is the process of splitting a nucleus into 2 or more fragments. Applications, they're far-reaching, but nuclear reactors are the most common, right? So those are slowly releasing energy. Nuclear bombs, on the other hand, that is a quick release of energy. And what's a good example? This is a good example. You've got uranium-235. We're shooting a neutron at it, and it's breaking apart into chunks. So the 2 chunks that it's breaking apart into, barium-141, krypton-92, and then we're getting 3 neutrons as a byproduct. So if we start with 1 neutron getting shot into a uranium-235 atom, we're making 3 more projectiles, which can then be used to, hit other uranium-235 atoms. And so that's kind of how a nuclear bomb works. You have this quick release where all these neutrons are able to hit other atoms and able to break them apart into other pieces. Nuclear reactors, on the other hand, absorb some of these neutrons. You have neutron absorbers that actually take the neutrons out so that this reaction can be stopped, and you don't just get a huge amount of energy being released that's out of control and that's going to blow something up. Again, here is a diagram of nuclear fission. Nuclear fusion, who discovered that? Mark Oliphant in 1932. Fusion was actually discovered first. What is it? It's the process of combining 2 smaller nuclei into a larger nucleus. What are the applications? Currently, stars do nuclear fusion and always have. Hydrogen bombs, though, also something that we've made. They use nuclear fusion as a way of making energy. So what is an example of that? You've got hydrogen-2, otherwise known as deuterium. You've got hydrogen-3, otherwise known as tritium. You put them together and you can make a helium nucleus, which is just a neutral helium. It's not an alpha particle, actually. It's helium-4, and then you get a neutron as a byproduct. And so that's what all early stars use as a fuel source, is combining hydrogens together to make heliums. Well, that's it. So if you have any questions, please let me know.